Hundreds of millions of years ago, our planet succeeded in creating a climate and conditions suitable for supporting life. For all those years, it's been making use of its self-cleaning capacity. Slowly but surely, residual matter from living organisms is washed out to sea as silt by the rain and the rivers. As the tectonic plates shift, the silt on the ocean floor melts into the hot core of the Earth. At these high temperatures, the residual matter breaks down into the basic elements of which it is composed. The Earth returns these elements in three forms: metals in the forms of ores and alloys, minerals in the forms of rock and obsidian, and gases that are released into the atmosphere when a volcano erupts. The gases are then cleaned from the atmosphere by the weather system. This washing water fertilizes the land and starts off the life cycle again. Our consumer society is growing at such a speed that the Earth cannot replenish itself fast enough and is gradually becoming exhausted. It's becoming ever more difficult to find the raw materials we need, and the remaining waste forms a huge problem. With the advent of microelectronics, we are able to make ever smaller, compacter, and more complex products. These products often contain many different and sometimes rare raw materials, which are difficult to remove and reuse. Many of our electronic devices end up on the rubbish dump or in the incinerator. We call this e-waste. At the same time, there is a shortage of the raw materials needed for electronic devices, particularly the so-called rare materials such as neodymium, europium and dysprosium. As these metals mainly come from China, the West is at a risk of ending up in a dependent position. For this reason alone, it's necessary to recycle e-waste as much as possible. And this idea fits perfectly with our goal of having no waste, the Zero Age. As early as the 1960s, a process was developed that is actually both a miniaturization and an accelerator of the Earth system of recycling its residues. This process is called elementary retraction. In several steps, residual products are processed in a way that returns the metals they contain to their pure form. The process delivers the same three product forms as the Earth: metals or alloys, obsidian, and gases. Resembling the process in the atmosphere, the gases are purified in a gas washer. The artificial fertilizer produced by this method is suitable for agriculture. In order to optimize the elementary retraction process, the right raw materials must be combined in the right proportions at the right time in an installation called an elementary retraction plant. This requires thorough knowledge of the chemical processes involved and a carefully calibrated mixture of residues. Only if these conditions are met will the process run successfully and completely transform the waste into the products mentioned. An elementary retraction plant is relatively restricted in size, but the small scale of the setup is sufficient to process the waste from 1 million affluent citizens. The setup is kept to a small scale to limit the transport of waste. The idea is that it is better to have one facility in each province than a few enormous installations that need long logistics lines for production purposes. The small scale also puts limits on emissions, industrial noise, supply and drainage, and light, and therefore restricts nuisance to the surroundings. The elementary retraction process uses raw materials that are worthless or even dangerous to society. By recycling these materials into usable and sometimes even precious raw materials, the process delivers positive results on all fronts. IVER, the Institute for Elementary Retraction, was founded in order to develop and optimize the elementary retraction technology, to export knowledge and technology, and to stimulate the reuse of e-waste. The elementary retraction technology provides a unique opportunity to the Dutch business world, giving a technological advantage to the idea of life without waste, the Zero Age.